If you needed any more proof that the world has, well, fundamentally changed in the last few years, just look at large language models. LLMs.
Oh, absolutely.
I mean, look at how fast they achieved liftoff. We're talking about systems like ChatGPT hitting 1 million users in, what, 5 days?
5 days. It's unbelievable.
And then it just roared to 100 million users in just 2 months. That's not just a success story. I mean, that's a growth curve we've just never seen before.
Not in tech, not anywhere.
Exactly. And we've all played with the conversational side of it, but today we're going deep. We're going under the hood.
Right.
We are going to peel back the layers and really examine the technical foundations that make this whole revolution possible. And our main source for this journey is a brilliantly accessible book called Hands-on Large Language Models.
By J. Alamar and Martin Grutendorst. It's a fantastic resource.
It really is. And what makes it so good is this intuition-first philosophy they have. They use a ton of visual language, helpful graphics. It just makes these really complex ideas stick. It doesn't feel like a dense textbook at all.
That's right. And that's our mission today. We want to give you a really structured understanding of LLMs. You're already a user, probably an expert user at this point.
Sure.
But understanding the core architecture, how raw text becomes a mathematical structure a machine can actually understand. That's what transforms you from just a user into a really informed participant in this whole AI era.
So let's unpack that. We're tracing the journey from, plain human language to the complex math a machine can process.
And that transformation, it begins with a step that sounds simple, but it is absolutely foundational: tokenization.
Right. Tokenization, that's a very first stage. Before an LLM can even begin to understand a sentence like, the deep dive is starting now, it has to break it down.
It has to chop it up into smaller, manageable pieces or tokens.
And in English, that's usually just splitting it by spaces, right?
That's the first step, yeah. Splitting on white space to get individual words or sometimes even subwords. And these unique tokens, they form the model's entire vocabulary.
So the vocabulary is basically a master list of every single unique word or piece of a word the model has ever learned.
Exactly. And that can be tens, even hundreds of thousands of unique tokens.
Okay, so the first attempts to turn that vocabulary into something a computer could count were, well, they were pretty crude, weren't they?
They were. The classic approach is the bag of words model. Once the text is tokenized, you just throw out the word order entirely.
You just count them.
You just count how often each word appears. And that count becomes a numerical vector.
But the flaw is right there in the name, isn't it? It's literally a bag of words. If you ignore the order, how much meaning are you actually throwing away?
You lose everything. I mean, think about it. 2 sentences. The boy chased the dog, and the dog chased the boy.
Okay.
A bag of words model would see those sentences as mathematically identical. Same words, same counts.
But they mean the complete opposite thing.
Exactly. So that kind of representation, it's just useless for capturing any kind of sophisticated meaning.
So we needed a way to inject meaning semantics into the numbers, not just counts. And this is where it gets really interesting with dense vector embeddings, stuff like word2vec.
Right. Dense vector embeddings are designed to capture those semantic properties. Instead of just counting, we represent a word numerically based on the properties it has.
Can you give us an example?
Sure. So a word like baby might score really high on numerical properties like newborn or small or human.
Ah, I see. And because of that, words with similar meanings like baby and infant, they end up being really close together in that multidimensional space.
Much closer than, say, baby and bulldozer.
Right.
But modern LLMs, they go one giant step further.
Yeah.
We've moved from those static embeddings to what we call contextualized embeddings.
What's the difference?
Well, a static embedding gives the word bank just one vector, one set of numbers. It doesn't matter if it's a river bank or a financial bank.
It's a single fixed meaning.
Correct. But a contextualized embedding, it assigns a different vector based on the word's context in that specific sentence. That dynamic context-aware ability is what lets modern LLMs do such complex things.
Wow.
And a fun fact here, these contextualized vectors are the fundamental engine that powers AI image generators like DALL-E. The model is understanding the semantic context of your text and then mapping that meaning to pixels.
That's a great connection. Okay, so we have these incredible contextual vectors that understand meaning. What are the actual architectures, the engines that put them to work? The source material makes a really clear distinction here between 2 main types.
This is a critical distinction, yeah. You have representation models and you have generative models.
Let's start with representation models, like BERT.
Right. So BERT and models like it are typically used for specific predictive tasks, like classifying text. The crucial thing to remember is they do not generate new text. They just create this highly descriptive internal representation of the input.
They're optimized for one job.
Exactly. Then you have the generative models, the GPT family. These are the ones everyone knows.
Because they're the ones that talk back to you.
Right. They generate text in response to your prompt. And the scale evolution here is just, it's mind-boggling. GPT-1 started with a modest 170 million parameters.
And then GPT-3.
Ballooned to 175 billion parameters. And that size, that volume of data, it fundamentally changes what a model can do.
It really does. So let's look at representation models in action. A classic example is sentiment analysis, classifying a movie review as positive or negative.
Perfect example. You can use a model like, say, Twitter Roberta Base, which was fine-tuned specifically for that. The question then becomes, how good is it?
How do you measure that?
We evaluate its performance using metrics from something called the confusion matrix.
The confusion matrix sounds pretty intense. So for anyone listening who doesn't work in data science, why is something like the F1 score a better measure than just plain old accuracy?
That's a great question because simple accuracy can be really misleading.
How so?
Well, accuracy might tell you the model got 90% of the answers right. But what if 99% of all the reviews were positive? The model could just guess positive every single time and get a super high accuracy score.
But it would have completely missed the one negative review.
Exactly. So you need more nuance. We look at two main concepts, precision and recall.
Okay.
Precision asks, of all the reviews the model said were positive, how many were actually positive?
So it's about being right when you make a prediction.
Right. And then recall asks, of all the reviews that were actually positive, how many did the model correctly find?
So that's about not missing anything.
Precisely. And the F1 score is the balance measure that combines both of those into one number. So when you see a high F1 score, like 0.80 row, you know the model is performing well across the board. It's not just guessing.
Okay, that makes sense. But if a generative model can also do classification just by asking it, is this review positive or negative, why do we still even bother with representation models like BERT?
Yeah, that's a good point. The short answer is specialization and speed. While a generative model like Flan T5 can handle that task beautifully, BERT is just. It's inherently faster, it's smaller, and it's more tailored for that one specific job. Think of BERT as the specialist and GPT as the expensive general-purpose powerhouse.
And the success of systems like ChatGPT came when developers took that instruction-following idea and just scaled it up with massive amounts of human preference data.
That process of refinement is absolutely essential.
Stepping back for a second, we're seeing this proprietary versus open source debate really heating up. You have models like GPT-4 and Claude on one side, and then Llama 2 and Phi 3 Mini on the open side. What are the core trade-offs there?
Well, the proprietary models offer ease of use. You access them through an API. That means you, the user, don't need a super powerful GPU. The company handles all the heavy computing.
But the downside is you're sending your data to their server, and you lose total control over the code and the model itself.
That's the trade-off. Open source gives you complete control, complete transparency. You can run sensitive data on it locally on your own network. The stark downside, though, is the hardware. You need a powerful GPU with a lot of VRAM video RAM.
And the price tag on that is something else. The source material mentions that training the Llama 2 family alone cost more than $5 million in GPU hours.
It's staggering. That $5 million barrier really puts the term open source into perspective, doesn't it?
It really does. It sounds like AI development has the same entry requirements as running a major movie studio. You need venture capital or a national lab.
Yeah, it highlights that the most powerful open models are really only accessible to the GPU-rich.
So speaking of control, let's dive into our third segment. How do you optimize the output of these generative models once you have them running? Because they're inherently probabilistic, right? They're just prediction machines.
Exactly. They generate the next token based on a likelihood score, and we can control that randomness using two key parameters, temperature and top EP.
Right. These are the dials we get to turn. So how does temperature change the model's behavior?
Temperature controls randomness, or you could say creativity. If you set the temperature to 0, the model does what's called greedy decoding.
Greedy decoding.
It always, every single time, picks the token with the highest probability. The output is predictable, often factual, but it can be really repetitive and, frankly, uninspired.
And if you turn it up?
A higher temperature allows less probable, more creative tokens to get chosen. It introduces that surprising, sometimes creative behavior we associate with these models.
And then there's top P, or nucleus sampling. That's a bit more nuanced.
It is. Top E is a cumulative probability threshold. It controls the subset or the nucleus of tokens the model is even allowed to consider. So if you set top P to 0.1, the model only looks at the smallest group of top tokens that add up to that 10% probability.
So if the top 3 words already account for 10% of the probability, it just ignores everything else.
That's a perfect way to think about it. It completely ignores the other options. By setting a low top EP, you constrain the model's choices, which usually leads to more focused, less rambling output.
Okay, so once we have the settings dialed in, the next step is maybe the most important skill in the industry right now, prompt engineering.
Absolutely. You can't just throw a simple sentence at a 175 billion parameter model and expect a perfectly structured report.
Right.
We have to think of the prompt as having modular components. The book breaks this down really well. You have the persona.
Act as an expert historian.
Exactly. Then the core instruction, the context, the format you want, the specific audience, the tone, and finally, the data for the task.
It's like giving it a highly detailed spec sheet for the job.
Precisely. And finding the best prompt is always an iterative process. You start simple, and you just keep adding and adjusting these components until you get the quality you want.
Now, for really complicated tasks, especially with math or logic, we need the model to do more than just spit out an answer. We need it to show its work. Which brings us to chain of thought.
Yes, chain of thought, or COTI. It's a clever method that enables complex reasoning by literally instructing the model to think step by step before it gives the final answer.
And just by adding that instruction, it gets better at logic problems.
Greatly improves accuracy. It forces the model to distribute more computational effort over the intermediate steps.
And then there's an extension to that called self-consistency. You sample multiple reasoning paths.
Yes. With self-consistency, you run the same question multiple times, letting the model think in several different ways. Then you just take a majority vote among the answers.
So you're trading speed for accuracy.
Big time. It increases performance significantly, but it's much, much slower.
Okay, so all these techniques optimize the model's own knowledge. But what happens when the LLM just confidently starts making things up, the whole hallucination problem?
That is where Retrieval-Augmented Generation, or RB, comes in. It's a really powerful solution for improving factuality. It basically stops the model from lying by forcing it to cite its sources.
So you're giving the model access to external verifiable documents to act as a fact check.
That's the core idea. The pipeline is pretty elegant. First, you take your external documents, could be company data, Wikipedia, whatever, and you convert all that text into numerical vector embeddings.
Like we talked about at the beginning.
Right. Second, you build a search index for those embeddings. Then, when a user asks a question, the system first retrieves the most relevant snippets from your documents. Finally, it grounds the LLM's response using only that retrieved factual text as its context.
So it's perfect for things like chat with your data. But does R completely eliminate hallucinations or just reduce them?
It dramatically reduces them. It confines any potential errors to the quality of the documents you provided. If your source material is wrong, the LLM will repeat the error, but it won't invent entirely new falsehoods.
And what's the biggest hurdle for someone thinking about implementing RAG?
Just maintaining that database. If your external information is constantly changing, like daily reports or new policies, you have to constantly re-embed and update that search index to keep the model's knowledge fresh.
We have covered a huge amount of ground here. We started with breaking language down into tokens, then turning those into dynamic, contextualized vector embeddings that actually capture meaning.
And we distinguish between the two main types. Representation models for classification, where we use the F1 score, and the generative models that rely on instruction following. And we hit on the real-world trade-offs between proprietary APIs and open-source models that need that huge VRAM investment.
And finally, we explored all the optimization strategies that give you, the user, control. From managing creativity with temperature and top to meticulous prompt engineering and boosting reasoning with chain of thought.
And of course, tackling the hallucination problem with RAG.
Exactly.
You know, what's truly fascinating is that the field is already moving beyond just text. We're seeing the emergence of multimodal capabilities.
Like BLIP2.
Right, which combines vision transformers with LLMs. This lets these models reason not just about text, but about images too. They can analyze a picture and describe its contents with incredible nuance.
That's amazing.
And this expansion, It reflects how we experience the world, right? Language doesn't live in a vacuum. Our understanding is always enriched by images, by tone, by visual context. As LLMs continue to integrate and reason across more data types, their capabilities they will continue to accelerate. It demands we think about how language links to all our other senses.
That is a thought worth contemplating. The foundational tech is already moving beyond language. Knowing the mechanics we've covered today is really the first step in understanding what that multimodal future is going to make possible. Thank you for joining us for this deep dive. Keep learning, and we'll see you next time.